All right, folks, it's Bass Action back in action here. On this page of notes, we are going to jump into the properties of logarithms. The reason that we're covering these is because when we get into the solving of our logarithmic equations in the next video, this is going to be a crucial step in the process. We can't solve most of our logarithmic equations without being able to properly condense. So let's jump into these, and our first three properties are going to be pretty clear and obvious. We've gone through them multiple times. So our first one, log base A of 1. The log of 1, we all know, we're shouting it out, is a giant 0. Then we're going to have log base A of A, and of course that's going to be 1. The next one, if we're looking at, we're taking the log on each side of an equation where the bases match, and if these are supposed to be equal and the base and the logs of the base and the bases are the same, then what I am taking the log of should also be equal. So these arguments will equal each other. So log on each side of the equation matching bases means that the arguments will also equal. Now, moving into our other properties, we've got r times the log of some number, okay? If we have this coefficient here, we can actually rewrite that coefficient as an exponent. So this log can be rewritten as log base A of m to the r power. The next one says that I have two logs. The bases of the logs are the same, and I'm adding those two logs together. This property tells us that we can actually write this as a single logarithm. So single logarithm with that same base, and instead of having the separate logs, we're going to write it as the single, and we're going to multiply the arguments. Now, I have a video that I've posted that proves why this relationship is true, so you're certainly more than welcome to watch that video if this seems like we're just kind of pulling it out of thin air. The next one is very, very similar. I've got two logs, same base. I'm subtracting them. So very, very similar relationship here. We can write that as a single logarithm. And instead of multiplying those arguments, we're going to divide those arguments. I don't have a video posted for this one, but if you understand the proof of the previous property, this one actually follows the exact same process. So now let's jump into how we would condense some logarithms, because again, this is going to help us when we're going through our solving process. So as I look through this first problem here, the thing that jumps out to me first is that I have this coefficient of a 2. I want to rewrite this coefficient as an exponent on that logarithm. So I'm going to rewrite this particular problem as the natural log of x squared plus my 3x plus my 2 minus my natural log of x plus 1 squared. Now remember, this does mean x plus 1 times x plus 1 with that exponent. That is going to come into play in just a little bit here. Now the next thing that I'm going to notice is that I have two natural logs and they're being subtracted. So using my properties from up above, I can write this as a single logarithm. And I'm going to divide those two arguments. Now, what is jumping out to me, because I have some experience and I've already done the problem, is the fact that this quadratic here factors. So I'm going to factor that out when I go to do my condensing. So that numerator is going to factor into an x plus 2 and an x plus 1. And then, since it's subtraction, I'm going to, in the denominator, I'm going to write this x plus 1 quantity squared. And I can even expand this out as an x plus 1 times an x plus 1. That's kind of helpful. It's going to make some things stand out for us a little bit. Now that I've condensed that down into a single log, I can see that, oh, I have an x plus 1 in both the numerator and the denominator, so those would cancel. So then I can write my final answer as the natural log of x plus 2 divided by x plus 1. And that would be our condensing into a single logarithm. Obviously, that's going to be easier to work with, and of course, in our solving process, it's going to become important. Looking at our next one here, the first couple things that stand out to me is this coefficient here. I would certainly like to write that as an exponent. I would also like to simplify this 5 squared minus 1. There's no reason to leave it like that. So we're going to do a couple things at once. So I'm going to say I have log of 8 to the 2/3 minus log, and just simplifying that, I'm going to have 25 minus 1, or in other words, log of 24. Now I can see that I have two logs. They do have the same base, and I am subtracting them. So I can write those as a single logarithm. So I can say log, and then I'm going to put the 8 to the 2/3 in the numerator. And again, this goes back to our algebra skills. What I'm going to recognize is that 8 can actually be written as 2 cubed. That's jumping out to me because that's the denominator of that exponent. So you've got to be comfortable simplifying those fractional exponents there. So I'm going to write that numerator as 2 cubed. And that, of course, is raised to the 2/3 power. So I just rewrote that 8, and that's all going to be divided by 24. Now, cleaning this up a little bit, my exponents here, my 3 times my 2 cubed, that's going to cancel. So this can be rewritten then as log. The numerator now becomes a 4, and the denominator is still the 24. That, of course, reduces, and my final answer is log of 1/6. Now, sometimes students are concerned that we're going to ask you to go from this log of 1/6 back to this. We are not going to have you do that, but you should be able to get from this to the log of 1/6. My last example on this page is certainly more complicated because I have many, many logs happening on this problem. So the first thing I'm going to look for is whether I have any coefficients. I don't have any coefficients I need to worry about. So I'm just going to start working from left to right. So I'm going to first condense these two logs because they're both natural logs, and I can see that I am adding them together. So since I'm adding those are going to condense to become the natural log. And I like to use some square brackets sometimes. So this is going to become the natural log of x squared plus 1 times my 9. And then I'm just going to rewrite everything else minus the natural log of x minus the natural log of 5. Now, the next thing I'm going to do is I'm going to combine the next two logs. So I can see that, okay, now I've got two logs here. Again, they're both natural logs. This time they're being subtracted. So when I condense that down, I'm going to have the natural log. And at this point, it'll clean up a little bit better for me. I'm going to have 9, I like to write it in the front, x squared plus 1. And then I need to divide that by the x, the other argument, and that's minus the natural log of 5. I'm down to 2 more logs that still need to be condensed. And what I don't want to have to do is have this fraction divided by something. So instead, I'm going to think this fraction times the reciprocal of this argument when I go to do that condensing. So I'm going to have the natural log of 9 times x squared plus 1, and that's divided by x. And instead of dividing by 5, I'm going to multiply by its reciprocal. So my final answer can be written as a single logarithm. The numerator is 9 times x squared plus 1. If you wanted to distribute that, you could, but it's not necessary. And the denominator will have the 5x. That is our final condensed. So the thing that I really want to caution you about here, that I knew that this problem was going to be more complicated, is the fact that we had this double subtraction here. This double subtraction should always cause a little bit of a red flag for you.